In this video, I will show you how to create a simple neural network using TensorFlow. My priorities are to keep it as simple and clear as possible, so we will be using only 50 lines of code and only one hidden layer. I'm using Python 3.5, TensorFlow 1.4, and I'm also using PyCharm 2.4, but you obviously don't have to use PyCharm. You can use IPython or whatever you are comfortable with. Our data will be the mnist dataset. And for those of you who aren't familiar with it, I have a quick preview here. These are 4 examples of the kinds of images we're using. It's handwritten digits, and the goal is to automatically identify and label them. So each image is 28 by 28 pixels, and since it's grayscale, we always have only one color value per pixel. And this is an example of the kind of neural network that we're building. This is from Wikipedia, and it'll be similar to this kind of structure where the input layer is going to be all of the pixels of one image, and then there's going to be a set of weight connecting every input node to every node in the hidden layer. And then there's going to be the output layer consisting of 10 nodes where each of the nodes represents one digit. So there's going to be 10 neurons in the output layer representing the digits from 0 to 9. Okay. So let's get started by importing TensorFlow. And since this is a standard dataset for neural networks, we can just import it from TensorFlow. And we're setting one hot to true here, and that means that the labels in the training and test data are not just the integers or the digits from 0 to 9, but each digit is represented by a vector of length 10, and it's all zeros and just 1, 1. The position of the 1 then indicates the identity of the label. So for example, for a 0 we would have 1 followed by 9 zeros, and then the digit 1 would be 0, 1 followed by 8 zeros. And that's pretty convenient here because we're gonna, as I said, end up with an output layer of length 10, and then it's easier to compare our predicted output to the actual labels. So the shape of our input is actually going to be 784 because the image that is size 28 by 28 pixels is actually going to be flattened. So if you imagine the image consisting of several rows of pixels, here they are just all combined into one long row of size 784. And hidden, that's the number of hidden nodes in our only hidden layer, and I'm going to set that at 200 for now. This is arbitrary. We can change it later to see how the performance changes, but just start out simple. Finally, n classes, that's 10 because we're dealing with the digits between 0 and 9. So this will not change. Alright, so now I'm going to add a number of functions, and in our main and the final function we're just going to call them in the same order as we're writing them now, so hopefully it will all be easy to follow. We'll call this MLP config. MLP stands for multi-layer perceptron. Oh, should add the def. And as inputs it'll take n input, n hidden, and n classes. So this is a function that will basically set up the network. So we're gonna tell it what kind of input to expect and initialize the weights, or start out with some random values for the weights that can later be tweaked. So x. X is going to be the color values of the images we feed in, and we're going to create a placeholder for the data that is going to come for now. tf.Placeholder, and it's going to be floats. This is the shape, and I think we don't actually have to give it a name for now. We won't need that, but since we can, I'm just gonna add it. So the shape of this variable for now is none and n input. So if we only had one image, it would be 1 and n input, so that's the number of pixels again. But we're going to be training in batches, and then in our test run, maybe we're going to feed in a different kind of batch size or a different number of images. So we can't fix, or we can't define the first element here in the shape right now. We're just going to leave it at none, which just means not defined yet. Actually, almost the same for y. It's also going to be floats. The shape now is going to be none and n classes. And we're just going to name it because why not? And we also need some weights. So we need two sets of weights. The first one is going to connect the input to the hidden, and the second the hidden to the output layer. And we're going to define them within a dictionary. So weights is a dictionary. It's going to have h1, random normal. Yeah, you don't have to use random normal, I guess, but it works. Again, since the first set of weights, h1, is going to connect the input to the hidden layer, those have to be the dimensions of the weight matrix. The same goes for the second set. It's okay to use random normal variables here, so it's basically just going to be noise, and then during the training steps this noise will be modified or adjusted to achieve better classification results. And then here we want to return x, y, and weights. Okay. Now in the next function, we call that MLP model. We're going to set up the layers. So here we need x and y weights. I'm not sure if we are actually going to need y. We'll see. So hidden. For the first hidden layer, or the only hidden layer actually, we're gonna have to multiply the input by the weights. And we do that by using matmul x weights, and then first set h1. And as you probably know, in neural networks you always have a nonlinear activation function. And we're going to use relu here, so we're going to add tf and a relu. So that's already included, and that's our hidden layer done. The output layer we're going to call logits. So logits equals. Here we're going to multiply hidden, so the output from the previous layer, and weights out. Note that I'm not including an activation function just yet, because we need the logits the way they are to compute the loss later. The logits represent probabilities, but they are not restricted to the range of 0 to 1, so they are unscaled probabilities. Yeah, we'll come back to that later. And finally, prediction. And then to get the prediction, we use argmax here to find the position of the largest value within logits. And we convert that into an int and convert the int into a one-hot vector. So just like the labels we imported. And so we want this to return prediction and logits. And the next function, we're going to define the loss, or compute the loss. And we're going to use softmax cross entropy with logits. So as you can see here, there are two slightly different versions of the softmax cross entropy with logits. There's the old one here. This one is actually not supported anymore. We're just going to stick with this one for now. So this function takes the logits, which, as I said before, they were unscaled, and it transforms them into a valid probability distribution. So they get transformed to be between 0 and 1, and their sum has to be 1. And the labels, these are the true labels of the data that we want to predict. Oh, and then since we are not only feeding in one picture but an entire batch, we have to average across all of these losses. So we just add tf.reduce mean. So at the beginning I was a bit confused by the reduce mean part, but it just means that you average. Okay, next we want to get the accuracy. Get accuracy. For that we need the prediction and the actual labels y. And a correct prediction is when the prediction gives us the same result as the real label. Meaning that the largest value within our prediction vector has to be in the same position as the largest value in y. And then in accuracy, we just average across all of the predictions within our batch. Okay, and that's basically all the individual functions we needed to call from our main. So we just need the main. And we start out from top to bottom. X, Y weights is equal to MLP config. Next one, prediction and logits. Alright, well, so far we just followed the structure of the functions that we defined above, and what we still have to do though is we need to use an optimizer to adjust the weights after every training step. We're going to call that train step. And we're going to use a gradient descent optimizer. This one here. And you have to give it a learning rate, which we'll set to 0.01. You don't have to use that either, just you can play around with it. And then we also have to tell it what to minimize, and we want to minimize the loss. And the TensorFlow session is kind of the environment in which you can do all those TensorFlow operations. You can work with these tensors. Yeah, it's just something that you need to start before your training begins. We also need something to initialize all the variables that we defined at the very top. So we're gonna call it init, and it's the global variables initializer. And then don't forget to actually also run that. Okay. And now we can actually do our training steps. And gonna put them in a for loop for I in range. And we'll just do 1000 for now. And as I've mentioned before, we're gonna do the training in batches, so we need to define a batch first. It will fetch a batch of size 1000. This is a very handy little function because it'll already fetch you a random set of images as a batch. Because if you have a lot of training data and the data is ordered by identity, so first you have all the zeros and then the ones and so on. And if you have more than 1000 zeros and you just grab the first 1000 and the next 1000, then you might end up with an entire batch full of zeros, and the model can't really learn anything about the differences between the digits if you just give it zeros. So you always have to make sure that you have a mixed or a random set of training data. And then we just want to sometimes have a printout to see how the network is doing. So we're going to do every 100th step. The printout we want is going to be the accuracy. Okay, I'll start at the end here, and the feed dictionary is the data that it uses to train, and as you can see, the batch already consists of 2 elements. And we're going to feed the first element in as x, the image, the color values, and the second element is the labels, so the 1 hot vectors. And at the beginning here, we need to give it a kind of an output, a requested output. So you can see here that my variable at the front here matches the accuracy there. So you will get an output that has the same format as this accuracy, but you explicitly have to call it that way because you can't just do session run and not specify anything as an output, but then still get a printout of that, because these things like accuracy, loss, and so on, they are all tensors within the TensorFlow system, and you can't just make them readable and printable. So if we want to have a print statement here, we need to explicitly access that variable from session run. Put in the step and the accuracy. Just to maybe show you what I mean here, if we just added accuracy, So this is the name of the variable within the session, and the ACC that I have in the first print statement here is the one that is explicitly called from session run. So we can have a look at that in a minute. And then this first case where we get the printout, that's not a real training step. So this is just to check the accuracy occasionally. And in every other case, we do session run, and then here we go train step, and the dictionary is actually the same as here. Okay, so the reason that I put in train step here is that this is basically the highest or the last step that we have to take in every training step. So if you run session run, it will only run those parts of the model that are necessary to calculate this variable that you input here. Right, so let's say you used loss here, then it would only calculate up to here, and it wouldn't even calculate the accuracy, and it wouldn't use the gradient descent optimizer. So that's the reason why we use train step here, because that is the last thing that's being computed, and it makes sure the whole model is run every time. Finally, we want to know how the model performs with the test data. We want to print out for that as well. Accuracy. We have to do another session run. Accuracy. Because now we're testing, we're not training anymore, so we don't need to update our weights anymore, we don't want to do that. We don't use the gradient descent optimizer in this step. And the feed dictionary is now not the training data, but the test data. So X will be mnist.test.images, and Y will be mnist.test.labels. Why is that still red? Because it's supposed to be part of the main. Okay. And finally, we just call the main here. Okay, well, let's see if this runs. So as you can see here, we get these weird, not super readable printouts: tensor, mean, 1, shape, and d-type. This is not very meaningful, so that comes from here, and it just shows you that you can't just print out the accuracy as such. You have to request it from the sesh.run, and the ACC, those are these values. So for example, this is an 81% performance, and those are perfectly fine. So I'm just gonna remove this and quickly rerun it, and then we can see better. So we start out with performance of 0.1, so that is 10%, which makes perfect sense for chance level because we have 10 digits, and probability of guessing one correctly is 10%. And then it actually increases pretty quickly, and we end up with a test accuracy of 83%. So that's not great if you compare it to other neural networks, but if you consider that we only have the one hidden layer and that we're just using such a short script here, I was actually surprised that the performance was this good. Now you can tweak things. You can, for example, increase the number of hidden layers. Sorry, hidden neurons. Let's put 500 here. Save that and run it. So before we had 83%, and now let's see. Okay, so now we end up with 86. I don't know if that was worth the effort. What would make more sense maybe is use an additional layer. But yeah, you can play around with that. Just one more note, this would not yet work with tensor board. You would have to add a few lines of code here and there to make tensor board work. Maybe I will do another quick video on that as well. But yeah, as I said, my goal was just to reduce one of my neural networks to the bare minimum that would just work and still be clear and have a kind of acceptable performance, so that hopefully you can understand every part of it and expand it however you want. Okay, thanks for watching.